Okay. Let's do a quick recap of what we went over last time. So last time we introduced the notion of the interior of a set. Using high-level language, what's the interior of a set?
It's the largest open set.
Yeah, it's the biggest open set you can fit inside of a set. Now its proper definition is it's the union of all open subsets of A. But the high-level way everyone thinks about it is it's the biggest open set I can fit in there. And then what's our high-level way of thinking about the closure of a set?
Smallest closed set that can contain it.
Yeah, it's the smallest closed set we can get that still contains all of A. Its precise definition is it's the intersection of all closed sets containing A. So that's its precise definition, but it gets you that logically equivalent notion you have in your head. So, and then remember, always and forever, A is always sandwiched between its interior and its closure. This is the biggest open set we can fit inside of it, so it has to be inside of A. And then this is the smallest closed set we can get containing A, so A has to be inside of it. Now we also proved that if A is equal to its interior, then A is open, because its interior is always an open set. It's the biggest open set you can fit inside of A. So if the biggest open set you can fit inside of A is all of A, then A is open, right? And similarly, if A is equal to its closure, then A is closed. If A is closed, the smallest closed set you can get containing A is all of A. You can't get any smaller than that, otherwise you lose some of A. So that was the interior of the closure. Now I told you this theorem 2.5 is going to come up. It's never going away. We're going to see this 1,000 times. A little bit of an exaggeration, but we're going to see it at least like 5 times today using theorem 2.5. What was theorem 2.5? This was a big theorem we proved last time. It was that if X is in the closure of A, that's logically equivalent to every neighborhood of X intersects A. Pictorially, let's come back down to this picture and get some intuition. So here's A, it's got these boundary points, not these boundary points, all the points in between, and then this weird handle coming off, right? There's A, here's its interior. This is in the standard topology on R2. And then here's its closure, right? We said a point is in the closure of A, so let's pick a point here. Here's a point that's not in A, but it's right on the boundary. There's our point little x. Is that point little x in the closure of A?
Yes.
Yeah, it shows up right here. It's in the closure of A. What this says is, it's in the closure in A if every possible open set I could draw around X intersects A. Notice that, draw that open set, if we draw it over here, we're always going to intersect A. No matter how small I make that open set around X, I'm always going to get some of A. That's when you know A is in the closure. So, A being in the closure is logically equivalent to every neighborhood containing X intersects A. Or let me just read out what this says precisely. For all neighborhoods of X, the intersection of that neighborhood and A is not empty. So they have a point in common. Their intersection is not empty. What's the intersection of two sets? It's all the points that are in both of them. So this is saying there is at least one point in both of them. Their intersection is not empty. Overstating it. And then this is just a contrapositive of this. If for it to be in the closure, every neighborhood has to intersect A. For it to not be in the closure, then there has to be at least one neighborhood that doesn't intersect A. So it's not in the closure is logically equivalent to there exists some neighborhood such that when you intersect it with A, you get the empty set. It doesn't intersect A. They have nothing in common. So these two are logically equivalent, and that's what theorem 2.5 gave us. And we'll be using that a few times today. And then finally, at the end of last time, we proved this. If we take remember what the complement is? What's the complement?
Everything that's not in the set.
Everything that's not in the set. And we kind of think about it like not. So if you take the complement of the interior of A, that's the same thing as taking the closure of the complement. So if I want to do the complement before my interior, it turns my interior into a closure. Similarly, if I take the complement of the closure of A, and I want to pull the complement inside and do the complement at first, that turns the closure into an interior. So just reading it out now, the complement of the interior of A is equal to the closure of A's complement. And the complement of the closure of A is equal to the interior of A's complement. You might remember I drew out the pictures last time showing you the sets and how they evolve to show you how you end up with the same thing. So you can go back and watch that to get a picture of that if it's not quickening your intuition. Okay, so that's reminding us from what we did last time. Now, the next section we're going into is limit points. And this is limits just like we talk about in calculus. There's two ways that I try and give people a rough idea of what topology is based off of their background education. If they've never done calculus before, I typically tell them topology is like rubber sheet geometry where you can stretch things out. And that's kind of what I told you guys. The way I tell it to a calculus student is that topology is like more general calculus. In calculus, you're doing an analysis of just a topology on the real number, or just a standard topology on the real numbers. That's all you're focusing on calculus. And so when you calculate a limit in calculus, it's a limit using the standard topology on the real number. We're going to talk about limits in general, limits for all topologies. And it just so happens that it's also going to give us limits for the standard topology on the real numbers. So the way we calculate limits in topology, they give you the way we calculate limits in calculus, but not vice versa. Make sense? So we're going to talk about limits. It's the exact same concept that we talked about in calculus, and eventually we're going to get to continuity. It's the exact same concept we talked about in calculus. When you take a calculus course, there's four big ideas in calculus. It's the idea of a limit, the idea of continuity, the idea of a derivative, and the idea of an integral. These are the four big ideas you talk about in calculus. So limits and continuity, we will talk about them in a more general sense than you do in calculus, but we'll point out their calculus equivalents. And then these two concepts, these are just special types of limits. A derivative is just a special type of limit, an integral is just a special type of limit. So it'll give you a good foundation, a more general foundation for going into a calculus class when you eventually do that. And the part of calculus that scares everyone is what we're going to talk about today. It's limits. That's the scary part. Once you get limits, the rest of this stuff ain't so bad. But limits is the part that scares everyone away. So not only are we going to talk about the scary part of calculus, we're going to do it in a much more general way than you do in calculus. So let's find out what's so scary about these things. So first definition of a limit point. Let A be a subset of a topological space X. I'll always use T dot S dot now for topological space because I write it so much and it takes so much space. Then some point in X is a limit point of A, provided that every neighborhood of X intersects A at a point other than X. That's a lot to swallow. Let's read it one more time. Let A be a subset of some topological space X. Then, some little point, notice that that point is not necessarily an A. Some point in X is a limit point of A, provided that every neighborhood of X intersects A at some point, not counting X. So intersects A at a point, but the point can't be X. It can be any other point, just not X. That's what it means for X to be a limit point of A. We use A prime to represent all the limit points of A. So A prime represents all the limit points of A. So what this definition is saying, here's it out written all densely. X is a limit point of A, is logically equivalent to for every neighborhood of X, when you remove little x from that neighborhood, so we take the neighborhood and we get rid of just point X, and intersect it with A, we're not empty. So our neighborhood intersects A at some point other than X. We have our neighborhood, we get rid of the point X, and it still intersects A. Now notice how close this right here is with this. X is in this set is logically equivalent to, for every neighborhood, some set intersects A. The only difference between it being in the closure and it being a limit point is they can't intersect at the exact point X. They have to intersect at a different point. So the limit point and the closure are very closely related. Okay, but with this definition, let's now start calculating some limits. Do a bunch of examples to try and get you a little bit comfortable with this notion. So we're going to go to the standard topology on R. With me? And we're going to look at the set A equal to 1 over n for every n in the positive integers. In other words, what is a set if we write out A explicitly? A is equal to, what are the points in here? We have 1 over 1. We have 1 over 2. We have 1 over 3, ... And we're just writing out all the 1 over n's, right? It's all those points. If we were to write it on the real number line, here's 0, here's 1. So we have the point 1, so that's this point. Then we have the point 1/2. Then we have the point 1/3. Then we have the point 1/4. Then 1/5. Then 1/6. Then 1/7. Then 1/8. ... Now what are all those points getting closer and closer to? 0. Will they ever actually reach 0? No. There isn't any n I can put down here such that 1 over n is 0. If n's a trillion, 1/1,000,000,000 still isn't 0. Okay, so there's our set A. We're looking for the limit points on A. We are looking for the points such that any neighborhood around that point has to contain other points in A. So let me show you a point that's not a limit point. 1 is not a limit point. How do I know? Here's an open set. Remember, we're in the standard topology on R, so our open sets are open intervals, right? So here's an open set. Does it intersect A?
No.
It intersects A at the point 1.
Oh.
One's in A, and one's in that open interval.
Yeah. Okay.
So it intersects A at the point 1. Does it intersect at any other point? No. So 1 is not a limit point. The only way 1 could be a limit point is if for any neighborhood of 1, it intersects A at a point other than 1. Is 1/2 a limit point?
No.
If I draw a neighborhood like this, okay, that intersected 1/2, that intersected A at more than just 1/2, right? We got all those points. But the only way it's a limit point is if every neighborhood we can draw around this point, every neighborhood of that point contains some points in A. So I chose a bad neighborhood. If I would have chosen this neighborhood, okay, now I didn't get any points in A. So 1/2 is not a limit point. It's only a limit point if for every neighborhood we intersect A at some point other than the point in question. So are any of these points going to be limit points?
No. Maybe 0.
0 is a limit point. 0 is not in A, but a point doesn't have to be in A to be a limit point of A. What does it mean for X to be a limit point? So some point in X is a limit point of A, provided that every neighborhood of X intersects A at a point other than X. So 0 is the only point. No matter how small of an interval I try and draw around 0, I'm going to get points in A that aren't 0. 0 happens to not be in A, but maybe it was in A. I could have just as easily said, this is all these numbers together with 0, and made 0 in A. 0 would still be a limit point of A. So whether 0 is in A doesn't matter for whether or not it's a limit point of A, because we're only interested in points other than 0. And no matter how small you make that interval around 0, you're going to get points inside of A that aren't 0. Right? Because this keeps getting closer and closer and closer to 0. So it doesn't matter how small of an interval you choose around 0. I'm going to make it so it just goes 1/1000th this way and that way. Just a real small number around 0. Well, then once we get to 1 over 1,000,000,001, we're now in that interval. So eventually we get there. So it doesn't matter how small you put that interval around 0, we're going to get it. So in this case, the limit point on A is just a set containing 0. That's its only limit point. Make sense? Let's try another one. Still standard topology. Now A is equal to the interval from 0 to 1. So all the numbers in between, including 0. What are the limit points? So let's draw it out on the real number line just to help us see it. So we got 0 here. We've got 1 here. We're including this, not including that, and including all the numbers in between. 0 is a limit point, for sure. No matter how small of an interval I create around 0, I am going to contain some points to the right of 0, which will be points in A that aren't 0. So 0 is a limit point.
It has to be to the right.
No, it's just in this case it is going to be to the right. If I create some small interval around 0, on the left I don't capture any points in A, but on the right I do. 1 is also a limit point. Even though it's not in there, any small interval I create around 1 is going to get some of the points of A to the left. So we got 0, we got 1. Anything else? What about 1/2?
I would assume so.
No matter how small of an interval you place around 1/2, you're going to get points in A other than 1/2. You happen to also get 1/2, who cares? You get points in A that aren't 1/2.
So everything in between 0 and 1.
So everything in between 0 and 1, including 0 and 1. So the limit points in this case are equal to the closed interval from 0 to 1, including 0 and 1. Right? Hey, let's move on to the next one. A is now the rational numbers in the standard topology. So what are the limit points now of the rationals?
0.
That's one of them. Because with 0, no matter how small of an interval I create around 0, I'm going to get other rational numbers, right? So 0 is a limit point.
So every point is 1 point.
Every point is a limit point. Because the rationals are dense in the real numbers. Yeah. The closure of the rationals is the reals. Or in other words, they're everywhere. You can't get away from them. Any little interval you take, you get infinitely many of them. So pick any point on the real number line you want, you're going to get infinitely many rationals. So you're definitely going to get some rationals that aren't the point you're talking about. So the limit points in that case would be all of R. Good?
Is infinity its own point, or does it just represent?
Infinity is not a real number. It's what we call an extended real.
By can't you have a limit that goes to infinity?
We define what this notation means when we say the limit of some function as x approaches x naught equals infinity. We define what that means. And this is not equals in the sense that this isn't some math operation saying now it's equal to this real number. It's notation to say that this function gets arbitrarily large.
Yeah.
That's what it means. So it's not actually equal to the number infinity because infinity is not a real number. So it's notation that we use to help us understand what the function is doing. If you want to handle infinity as a value, you have to do analysis on what's called the extended reals, which you don't do in calculus. You're just working with the reals.
Okay.
So infinity, it's a symbol you use, but you don't treat it as a number. You don't do operations with infinities. Okay. All right, so let's do our first little theorem here. Sorry, I really squished it in. I didn't realize how many lines I was going to take. All right, so let X be some topological space, and let A be a subset of X. Now, reminder, when I call X a topological space, what am I saying? I'm saying X has some topology that we're not going to bother stating it. But really, X together with tau is a topological space. We're being super lazy. Get used to that because it's the common way that most math authors will say it. They'll just say, let a set be a topological space. What do they mean by that? There's some associated topology. We're not going to bother stating what it is. So let X be a topological space and let A be a subset of X. Then the closure of A is equal to A union together with its limit points. Take A, add all its limit points, you get the closure. Now you could almost guess this. Well, I shouldn't say that. We'll see exactly how it comes together, but shouldn't be too surprising seeing how this definition for x being a limit point is so stupid close to what it means to be a closure point. Really close to each other, so this shouldn't be too surprising. So how am I going to prove it? I'm going to prove that they're subsets of each other. I'm going to show that if x is in here, then it's in one of those two sets. If it's in one of those two sets, it's in the union. And I'm going to show that if x is in one of those two sets, then it's in here. That's the logic. All right, so let's jump through it. So let x be a point in the closure. Now, if x is in the closure, it's already possible that's in A, right? So let x be a point in the closure, and observe that if x is in A, we're already done. Then x is in A union A's limit points. So now we're going to handle the case where x is in the closure of A, but it's not in A. So we handled if it's in the closure of A and it's in A, we're done. Now we're going to handle if it's in the closure of A, but it's not in A. Then is it still in here? So that's how we got to continue now. Okay, so now assume that x is not in A. So we got x is in the closure of A, but x is not in A itself. So it's one of those boundary points, right? And observe that by theorem 2.5, the one I told you we're going to reference a billion times, then what? X being in the closure means for every open set, for every neighborhood of X, that neighborhood intersects A at some point. Right? Now we know that X is not in A. So I know this neighborhood has a point in common with A, and I know that X isn't in A. So whatever point these two have in common can't be X. So I know this neighborhood and A have some point in common. Maybe millions of points, but they have at least one point in common. I know that X is not in A. X is not in A. So if I remove X from our neighborhood, it still intersects A. I didn't get rid of the point that they intersect at if I remove X. Does that make sense? That's the logic going from this line to this line. So, since every neighborhood of X intersects A at some point, and since X is not in A, so it can't be the point where they intersect, then for all u sub X minus the set containing X still intersects A. If we get rid of X, we couldn't have gotten rid of the point where they intersect, because X wasn't in A to begin with. Okay, so that's how we're going from here to here. The only difference between this and this is we say it's still true even if we remove the point X. U sub X and A have something in their intersection. X isn't in A, so it can't be in their intersection. So if we get rid of X, they still must have something in their intersection. Okay, and then that's exactly what it means for X to be a limit point. So X is in A prime, right? So I just barely showed that A closure is a subset of A prime, or of A union A prime. Just barely showed if it's in here, then it's in here. So we did one direction. Now I gotta go the other way. I gotta show that if X is in here, it's in here. Okay. So now let's assume that X is in A union A prime. So it's either in A or it's one of its limit points. That's what we know about X. Now, if X is in A, is it in A closure?
No.
If X is in A, is it in A closure?
Absolutely.
Yeah, if X is in A, we already know it's in A closure, so that case is easy. So we're saying assume X is in A union A prime, which means it's in here or it's in here. If X is in A, obviously it's in the closure. So the only question now is, if it's a limit point, is it still in the closure? Okay. So now let X be in A union A prime, and note that if X is in A, then obviously X is in A closure, and so we're done. So now let's just handle the case where X actually is in A prime. So if X is in A prime, what does that mean? That means for every neighborhood of x, that neighborhood minus x intersects A. Now if that neighborhood minus x intersects A, then that neighborhood intersects A. If you intersect A when you're missing a point, you still intersect A when I give you that point. I just give you more points you could have possibly intersected A at. So, if x is a limit point, I know that for every neighborhood of x, that neighborhood minus x intersects A, and so that neighborhood definitely intersects A. Because even when it was missing a point, it still intersected A. So putting that point in, it still intersects A. Well, that's exactly what it means to be in the closure of A. So we showed if it was in A, it was in the closure of A, and we showed if it was a limit point of A, it was in the closure of A. Therefore, those two union together are a subset of the closure of A. So we showed that's a subset of that, and that's a subset of that, therefore the two sets are equal. Follow that? All right. Quick corollary of that now. What's a corollary? A proof that almost falls for free. It's like you almost don't even have to think about it. So here comes a nice easy proof now that follows from that. You're always happy when you see corollary. All right, corollary 2.9. Let X be a topological space and let A be a subset of X. Then A is closed if and only if A contains all of its limit points. It's closed only if it contains all its limit points. All right, so let's prove this direction first. Let's show if it's closed, it contains all its limit points, and then we'll show if it contains all its limit points, it's closed. Assume A is closed. A is closed, then what's its closure? A, it's its own closure. We just really showed that the closure is equal to A union all its limit points. So, then A is equal to, A closure is equal to A union all its limit points. And so it contains all its limit points.
Yes.
Ah. We like corollaries. All right, let's go the other way. Let's show that if A contains all its limit points, then A is closed. Let's assume that all the limit points of A are a subset of A. A prime is a subset of A. If I union a set with its subset, what happens?
You get itself.
You get itself. If I take everyone in this room and I union it together with the set containing me, what are we left with? Everyone in this room. So, since A prime is a subset of A, then A is equal to A union A prime. But that's also the closure of A. A union A prime is the same thing as the closure of A. So A is equal to closure of A, which means A is closed. Good? All right. Definition 0.30. You notice that we were in chapter 2, we're jumping all the way back to 0. Now, unfortunately, I don't think you guys went and got caught up on chapter 0, did you?
No.
Which is not good. Because chapter 0 is where we introduce a lot of notation and definitions that were going to be sprinkled throughout the course. So here's a definition of a sequence back from chapter 0. Let's re-go over it. We already did this earlier in the class. We're going to do it again. Sequence is one of those ones that, I don't know, the first couple times you come across it, it's confusing until you get it, and then it just seems stupid every time someone re-explains it. I guess that's how a lot of math goes up. Okay, so definition. Given some set X, a function f, I told you that we were going to see this notation always and forever. I know we've taken a little bit of break from this notation. Once we start talking about continuous functions, it's never gone away. So this notation, dense notation, gotta get used to it. F is a function from this set to this set. It maps everything in this set to something in this set. So, given x, a function f from the positive integers to x is called a sequence on x. So a sequence on x can always be written as 1 goes to something in x. We'll call x of 1. 2 goes to something in x, x of 2. X of 2 could be the same thing as x of 1. It could be different. It's just something in x. 3 goes to x of 3. 4 goes to x of 4. N goes to x of n. We create a function pairing every positive integer with something in x. That's a sequence. That's a sequence in x. Okay, So there's our sequence. Now, we don't need to write out the entire function like this. If we just use, instead of a set, use a list, so parentheses means now we care about order. Remember, when you have those brackets, that means order doesn't matter. If we put parentheses, we say now order matters. So if we want a shorthand for writing this out, we can just say, we'll just put whatever 1 paired with first. We'll just put whatever 2 paired with second. We'll just put whatever 3 paired with third. And so when you look at it this way, you instantly know, wait, what paired with this? 2 paired with this. What paired with this? 1 paired with this. So it preserves all that information, and you just list them out. And then if there's some general way of listing them out, we usually just write it in parentheses like this, call it x of n. So let's get a concrete example, because that was a lot to say. I'm going to create a sequence on the real numbers. So my x now is going to be the real numbers. I'm going to pair something, some positive integer, with a real number over and over again. Where 1 with a real number, 2 with a real number, 3 with a real number. That's a sequence. So, example, f is a function from the positive integers to r. So we already know, oh, it's a sequence on r. That's the definition of being a sequence on r. It's a function that looks like that. This particular function maps this way. We map f of n to 1 over n. So 1 goes to 1 over 1. 2 goes to 1 over 2. 3 goes to 1 over 3. And so you now know what every positive integer is paired with. If I say what's 1,000 paired with?
1 over 1,000.
1 over 1,000. That was tricky. All right. So if we were to write out the function explicitly, here it is. 1 goes to 1 over 1. 2 goes to 1 over 2. 3 goes to 1 over 3, dot, 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 n goes to 1 over n. Or, using our more dense notation, when we just list it out, then it's 1 over 1, 1 over 2, 1 over 3, dot, 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 1 over n, dot, 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 dot. Or we just write it as a sequence 1 over n. And notice how this gives you all the information you need to talk about the sequence. If I say, look at the sequence 1 over n, you instantly know the 5th term in the sequence. It's 1/5. So that is our notation for writing sequences. So when we're talking about some general sequence, we don't know specifically what the sequence is. It will look like this. When we're talking about a specific sequence, we'll write it out something like that. And you'll know what it is. I could have just as easily said, let's look at the sequence n squared over n cubed. There's another sequence. The first term in the sequence is 1 over 1. The next term in the sequence is 2 over 8. Or sorry, 4 over 8. The next term in the sequence is what?
8 over 16.
Try again.
3 over 32.
Try again. What's 3 squared? 9. What's 3 cubed?
Oh, yeah.
27.
27.
Oh, I see. But
Now you'll notice that all of these reduce. 1 over 1 is the same as 1. 4 over 8 is the same as 2. 9 over 27 is the same as, oops, 1/2 I meant. 9 over 27 is the same as 1/3. And then it would have been 1/4, 1/5, 1/6. It turns out I gave you the exact same sequence. Because n squared cancels out with 2 of the n's down there, leaving us with 1 over n. It's the same thing. All right. Anyways, so there are some examples of sequences. One of those things that you'll remember and then it'll come back to bite you. There's always some subtleties working with sequences that you forget to take into consideration. Okay. Oh, I already said that, but I'll say it again. No, I'll use this for an arbitrary sequence. We're talking about sequence, but we don't know what it is. I'll represent it with x of n. So when you see parentheses x of n, we instantly know, oh, this is some sequence. We just don't know what the sequence is. Okay. Now back to the material, 2.10. We just jump back to chapter 0 to remind yourselves of what a sequence is. Now we're coming back to chapter 2. So if you were trying to follow around in the book, follow along in the book, you wouldn't have seen this in the book.
I think we might have been there for that one. That was like our first one or something.
Oh, that's great. So you get the double dip. Okay. Next definition. If X is a topological space, then a sequence x of n in X is said to converge to some point in X, provided that for every neighborhood u sub x, there exists a positive integer big N such that our sequence is in that neighborhood from big N onwards. we call x the limit of the sequence. That was a lot to swallow. Let's do that again. Let me move the camera first so that we have that scribble space. But this right here is what's meant by a limit in calculus. So now we're getting to the calculus stuff. All right. Intuitively, the point that a sequence converges to is the point it gets arbitrarily close to. So now if we look at the sequence 1 over n, so 1 over 1, 1 over 2, 1 over 3, 1 over 4, what is that getting arbitrarily close to? 0. So the way a calculus student would write that is that they would say the limit as n approaches infinity is equal to 0. That's what they'd say. Now it's, obviously this is using the standard topology on the real numbers, right? So keep that in mind. So now let's understand the same concept using our actual definition that we have written out here. Because it's a lot to say. So we're saying, here's 0, here's 1. So x sub 1, in our case, is right here. It's 1 over 1. X sub 2 is right here. That's 1/2. And we have x sub 3 is 1/3. X sub 4 is 1/4. And we have x sub 5, x sub 6, getting closer and closer and closer and closer and closer. Right here we have x sub 100, somewhere right there. Obviously, not to scale.
So x is your limit, and it's just labeled here.
X is 0. X is equal to 0. X sub 1 is the first term of our sequence. X sub 2 is the second term. So x sub 100 is 1/100th. So this sequence keeps going. 1, 2, 3, And I can't write out all the infinitely many because there's infinitely many. If this is our sequence, then what is x sub 100 equal to? 1 over 100. Let's think about x sub 0, 0, 0, 0, 0, 0. Okay, that's such a stupid small number, right? 1 over that number. So if I try to plot that point's right here. Right? It's just to the right of 0. I can't plot it.
Yeah.
Right. So here's our sequence, and it's suddenly getting super close to 0. So this sequence is going to converge to 0. That's what it's going to converge to. So now let's understand our definition and see how our definition says that. What our definition says is, pick any neighborhood around 0 you want. Doesn't matter how small. Now, I'm going to draw it kind of big so that we can actually see it. So we pick some neighborhood around 0. In this case, it's going to be an open interval. I guess I'll just draw it here. Some open interval around 0. There it is. You with me? So we have some open neighborhood around 0. We are saying that our sequence converges to 0 if for any neighborhood of 0, there comes a point in our sequence. There comes a point in our sequence. You don't have to find the first point, just pick some point. So I'll say it's this point right here. There is a point in the sequence such that from that point onwards, we're always in the neighborhood. So the special point here, so maybe this was the point x sub 100. Okay? Notice that we could have started quarterback here from x sub 3 or x sub 5 or whatever that is. X sub 5 was in there, but so is x sub 100. Doesn't matter which one we find. You just need to find some point in the sequence inside the neighborhood such that from that point onwards, we're always in the neighborhood. If you can do that, then the neighborhood, or then the sequence converges to that point. Let's say that again. The sequence converges to a point if for any neighborhood containing that point, there comes some point in the sequence such that from that point onwards, we're always in the neighborhood. We call that special point x sub big N. Big N is that term. It's the big nth term. We're saying from big N onwards, it's always in there. So if I'm saying from x sub 100 onwards, it's always in there, then my big N is 100. You might say, okay, now find it for this neighborhood, and you draw a really small one. and I zoom in and I look close and I say, I notice that from the 10,000th term onwards, my sequence is always in that neighborhood. So for any neighborhood you choose around 0, I can always find a really big n such that from the nth term in the sequence onwards, we're always in your neighborhood. Right? It's a game you can't win. The game is you're trying to come up with a neighborhood such that I can't find a big N, such that my sequence is in the neighborhood from that point onwards. So that's the game you think of in your head when you think about how to do these. For any neighborhood someone gives you, your job is to try and find some big N, such that from that big N onwards, the sequence is always in that neighborhood. That's what it means to converge. So now let's read the definition one more time, and you'll see we're almost saying the exact same thing. So if X is a topological space, then the sequence X sub n in X is said to converge to the point little x in big X, provided that every neighborhood U sub X, for every neighborhood U sub X, there exists some positive integer big N. Maybe it's 100, maybe it's 10,000, maybe you have to go to the 10 trillionth term, doesn't matter. There is some big N such that our sequence is in the neighborhood for all little n greater than or equal to big N. So if big N is equal to 100, then what am I saying? I'm saying x sub 100 is in the neighborhood. I'm saying x sub 101 is in the neighborhood. I'm saying x sub 102 is in the neighborhood, ... I'm saying everything from big N onwards in our sequence is in that neighborhood. It's really dense. It's a lot to take in. We're going to read it one more time. Hopefully you got it. So let X be some topological space. Then the sequence Xn in X is said to converge to the point little x in big X, provided that for every neighborhood U sub X, for every neighborhood containing X, there exists some positive integer big N, such that the sequence is in the neighborhood from that big N onwards. We call that little x the limit of the sequence. We call it the limit of x sub n, and we write it out exactly like this. Like that. The limit as n approaches infinity of x sub n is equal to x. That's the notation. Okay. That was a lot. Now I'm going to write out the definition 4 times. 2 of them only apply to the standard topology on R, so it's the limit, it's the definition from calculus. So, here we go. The limit as n approaches infinity of some sequence is equal to x equals x is logically equivalent to, for every neighborhood of x, there exists some positive integer such that from that positive integer onwards, our sequence is in the neighborhood. 3 quantifiers, there's a lot to swallow. Let me read it one more time. The limit as n approaches infinity of x sub n is x, or in other words, our sequence converges to x, is logically equivalent to, for every neighborhood of x, there exists some large number n, some positive integer n, such that from big N onwards, our sequence is in our neighborhood. Now, a way that's more commonly written is to group this quantifier over here. I don't know why, it's just common. So let me say it that way now. It says the exact same thing. But maybe it'll help with clicking your intuition a little bit better. If you already understand that, that's a perfectly fine way to say it. Same thing again. Or in other ways we can say it. So x sub n converges to x means that for every neighborhood of x, there exists some positive integer n, some big positive integer n, such that our sequence is in our neighborhood from big N onwards. It says the same thing. For every little n greater than or equal to big N. Little n is the nth term of our sequence. So if big N is 100, then we're saying x sub 100, x sub 101, x sub 102. Those are all in our neighborhood. Okay. Now, in the standard topology, we can create neighborhoods with open balls, right? So, now going to the standard topology on R, what does it say? This same definition is for every epsilon, for every radius you pick for your open ball. So that's why it's going to be the same as a neighborhood. For every neighborhood, or for every radius you choose to pick around your open ball. Every radius you pick around the point. there exists some positive integer n such that x sub n is in that open ball. Remember, we're talking about a one-dimensional open ball, which is just an open interval on the real numbers. So such that our sequence is in that open ball from big N onwards. Now that's almost how you see it when you take a calculus course. Here's how you actually see it. So let me make sure this makes sense for a second. Maybe you already see it. If I want to talk about on the real number line, the distance between 2 points, B and A, how do I calculate their distance?
A minus B.
In this case, A minus B works, right? So the distance between the 2 points, A minus B, that works. But what if B would have been this point over here and A would have been this point?
Couldn't you just take the absolute value?
Right. Rather than having to keep track of order, we just say, let's just talk about the absolute value. The absolute value of A minus B, that's the distance. So take one minus the other, and then take its absolute value. That way if it comes out negative, it turns it positive no matter what. Or if we go back to our Euclidean metric, we can still use our Euclidean metric. Remember how we calculated a distance in 2 space? We said the distance between any 2 points, x and y, is equal to the square root of their first coordinate, the difference of their first coordinates, squared, plus the distance of their second coordinates, squared. That was the distance formula. You remember that? Do we need to see it real quick where that came from? It's worth it if you don't remember. Okay, so let's just do this for one dimension then. So if we were talking about one dimensional, the distance between x and y, what is that equal to? That's equal to x's first coordinate minus y's first coordinate squared. And then they only have a first coordinate because it's one dimensional. And the square root of a difference squared is the same thing as the absolute value of x1 minus y1. Because it always makes it positive. In other words, the square root of x squared is the same thing as the absolute value of x. Pick 3. What's 3 squared? 9. Square root it, 3. Pick 3. What's the absolute value of 3? 3. Let's try negative 3. Negative 3 squared is? Now take a square root, 3. What's the absolute value of negative 3? 3. So notice that this is still the exact same thing as the Euclidean metric. I told you the Euclidean metric works for any number of dimensions. If you're in R10, then you just do this for all 10 coordinate points. If you're in R2, here's how you do it. That's when you see the most. If you're in R1, it still works. It just turns out it's the exact same thing as the absolute value function, and so most people use the absolute value function. Okay. So notice that if xn is in the open ball, let's draw a picture of this open ball. So here's x. So x minus epsilon is epsilon to the left. So if this is x minus epsilon, that's epsilon to the left, and then x plus epsilon is up here, right? So our open ball goes to there, not quite including that point, sorry, and goes to there, not including that point. It's that open interval. You with me? Now, if a point is inside this open interval, what's the furthest it can be away from x? Epsilon. It has to be less than epsilon away from x. These are all the points less than epsilon away from x. They're all the points whose distance from x is less than epsilon. The point right here is a point whose distance from x is exactly epsilon. And the point over here is distance from x is more than epsilon. Epsilon is this far, which is the same as this far. You with me? So, if x sub n is in the open ball centered at x, that's the same thing as saying the distance from x sub n and x is less than epsilon. The absolute value of a difference gives you the distance. So the distance from x sub n and x, the distance between them, is less than epsilon from n onwards. So that's the only difference going from here to here. And so when you take calculus, this is the definition you see. Go ahead.
Can you give me the direct epsilon delta definition and let me compare it to that one?
The epsilon delta definition is the definition for the limit of a function at a point. It's not just the limit of a sequence.
you still be willing to put it up so I can compare the two?
We will go over the epsilon delta definition when we do continuity.
Oh, okay, so we will get that.
We will get that.
Okay.
So this is when you are just proving that a sequence converges to a number.
Okay.
Just the limit of a sequence. That's the definition. Epsilon delta definition, we don't cover that until we go over continuity, because it's really the criterion for continuity. The calculus textbook is just so afraid to introduce a limit to you too early that they hold off as long as they can and then give you the epsilon delta definition for the limit of a function at a point and in continuity at the same time. Because then continuity, a function is continuous at a point if the limit of the function at that point is equal to the value of the function at that point. And so they hold off as long as they can. And then they give it to you how it's most convenient at the time. But that's typically used as a criterion for continuity, not a limit. Okay.
Got the proof.
We did this. Okay. That was nothing. That's what's confusing me. Okay, and this is now nothing. Alright, so there we go. Full-fledged calculus definition of a limit. That's the big scary bad guy in calculus. Everything else is just applications of that for the most part. Okay, so now let's do a proof. In the standard topology on R, the limit as n approaches infinity of 1 over n is equal to 0. I already tried to give you intuition for this. Now I'm going to show you the actual proof of it using the exact definition now of convergence. Okay, so what am I trying to show? I'm trying to show exactly what we have right here. I'm trying to show that for any neighborhood of x, I can find some positive integer n such that from that integer onwards, our sequence is in the neighborhood. So here's our sequence. We're proving it converges to 0. So our neighborhood is going to be a neighborhood containing 0. So we're not talking about u sub x now, we're talking about u sub 0. For any u sub 0, I need to find some big n such that our sequence, or such that from that big n onwards, our sequence, 1 over n, is in that neighborhood containing 0. So we're replacing our x with 0 and our x sub n with 1 over n. And we're trying to show that this holds. Okay, so I need to do it for any neighborhood containing x. So let u sub 0 be any neighborhood of 0. So I need to show it for any neighborhood of 0. I can find some big n such that from that big N onwards, our sequence is in the neighborhood. Okay. Now, if we're in the standard topology on R, so I'm going to be using open balls, right? So, if O is in the neighborhood, or sorry, if U sub O is at U sub 0, I just want to call that U not so bad. Okay. If U sub 0 is an open set containing 0, then there must exist some open ball with some radius epsilon. There must be some open ball containing 0, such that that open ball is a subset of our neighborhood. So I've got 0 here. Here's 0. 0 is a part of some open set containing it. Maybe that open set is, that open interval together with that open interval together with some open interval over here. Okay, some arbitrary open set. There's a neighborhood of 0, some open set that happens to contain 0. We already showed before that in any Rn, if there's an open set containing a point, we can create an open ball containing that point that's a subset of the open set. So I'm guaranteed I can find an open ball centered at 0. With some radius. I don't know what radius it will have some radius. Maybe my open ball is that whole thing. Maybe it's some smaller portion. Maybe that's my open ball. So now here's my open ball. This is going to be my ball centered at 0 with some radius epsilon. Notice that this is the same thing as the open interval from negative epsilon to epsilon. Same thing in this case. I don't know what that epsilon is. I don't know how small of a radius we need to be inside our neighborhood. But I know that there is some radius that gets us inside the neighborhood. That's what we know. So then there must exist some open ball with some radius epsilon naught centered at 0, such that that open ball is a subset of our neighborhood. I'm going to prove, I'm going to show that our whole sequence, starting at some point, our whole sequence is in the open ball, therefore our whole sequence is in the neighborhood. So from here on out, I'm going to prove, I need to find some big N such that our sequence is in this open ball from that point onwards. So I know our sequence starts at 1, starts over here at 1, right? Remember, this is our sequence. And we got 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9. Maybe it's at 1/9 that we care about. So I need to show that there is some number, like n equal to 9, such that from that point onwards, our sequence is always in that open ball. So I need to find the big N. That's typically the crux of these types of proofs. Now, unfortunately, you probably haven't heard about this property before. It's kind of assumed that you would come across it before this class. No one your guys' age is taking this class. Most people doing this are in their 3rd or 4th year getting a math major. Anyways, so the Archimedean property simply states that there is no biggest natural number. There's no biggest integer. That's what it says. So any number you pick, I can always find an integer bigger than it. That's all it says. It's called the Archimedean property. So by the Archimedean property, there exists some natural number, some positive integer, such that it's bigger than 1 over epsilon. Okay, that's kind of weird. Why did I say that? Notice that epsilon is most likely going to be a really small number, right? And so 1 over epsilon is most likely going to be a really big. If epsilon is small, 1 over epsilon is big. The bigger the denominator is, the smaller the total number is. What's bigger? 1 over 1,000 or 1 over 1/1000? You know, when you divide by fractions, that's the same as multiplying by their reciprocal. So this is the same as 1 times the reciprocal of this, 1,000 over 1. So what's bigger, 1/1000 or 1 over 1/1000?
I think it's the second. The left is bigger.
1 over 1,000 is 1/1000th. Look, let's go back to how you thought about this when you were in 3rd grade. How many 1,000s can you fit in 1? How many 1,000s can you fit in 1? If you have 1 pizza and you have 1,000 people to feed, how much pizza does each person get? 1/1000. They get a sliver of a sliver of a sliver. Those poor kids, they got nothing. If you only have 1 pizza and you got to give it to 1,000 people, you're in trouble. Right?
Unless you're Jesus.
On the other hand, how many 1,000ths are there in 1? How many 1,000ths of a meter can you get in 1 meter? Or in other words, how many millimeters are there in a meter? 1,000. So this is 1,000. This is 1/1000th. They're very different from each other. Small number, big number. Okay. Back to this. If epsilon is a really small number, then 1 over epsilon is a very large number. So I'm saying it doesn't matter how big 1 over epsilon is, the Archimedean property guarantees me there's some number bigger. Right? So I'm guaranteed that there is some big number n greater than 1 over epsilon. Why am I phrasing it that way? I'm going to do some math here. I'm going to divide both sides by big N and multiply both sides by epsilon. You with me? Divide both sides by big N, multiply both sides by epsilon. That gets me this. I take this side and I divide it by big N. What's big N divided by big N? And then multiply it by epsilon. We're left with epsilon. Over here, I multiply this side by epsilon. Epsilon times 1 over epsilon is 1. And then multiply it by, and then divide it by big N. So I took both sides, divide it by big N, and multiply it by epsilon. That's how I get here.
Isn't the sign supposed to switch?
saying the inequality.
The inequality only switches when you multiply both sides by a negative number. And that's really easy to prove. If A is less than B, if I add the same thing to both sides, it doesn't change it. And if I subtract the same thing for both sides, it doesn't change it. If you have more money than me, and we both pay $1,000, you still have more money than me. If you have more money than me, and we both gain $1,000, you still have more money than me. So, start with this. Let's add A to both sides, and then subtract B. Oh, sorry. Let's subtract A and subtract B from both sides. So take this side. Let's minus A from both sides first. And what are we left with? A minus A is 0 is less than B minus A. Now subtract B from both sides. What do we get? We get negative B is less than negative A. So if A is less than B, then negative A is greater than negative B. Or in other words, if I multiply both sides by a negative, I need to flip the inequality. That's the only time you flip the inequality, and that's how easy the proof is for it. We were in here. Okay, so it doesn't matter how small or how big 1 over epsilon is, there is some number big N bigger than it. This big N is going to be my big N here. So, oh, I already walked you through the algebra on that. Multiply both sides by epsilon, divide both sides by N. So now notice 1 over big N is less than epsilon. Now, let's remember the picture for our open ball. So our open ball is centered at 0, and it goes epsilon this way. So this is the point right here, negative epsilon. And it goes epsilon this way. So this right here is the point epsilon, right? If 1 over big N is less than epsilon, 1 over big N has to be somewhere in here. Right? Now, our sequence is 1 over N. So the first term in our sequence, right here, this is x sub 1 is the same thing as 1 over 1. Over here, x sub 2 is the same thing as 1 over 2, right? 1 over N is a term in our sequence. It's the same thing as x sub big N, right? So x sub big N is a term in our sequence inside the open ball, right? Now, notice if we look at now, if I make the N here bigger, then I make my whole number smaller. So if I look at all the numbers 1 over N, where N is greater than or equal to big N. If I look at all the little n, where n is greater than or equal to big N, all the terms 1 over N, where n is greater than or equal to big N, how does that compare with 1 over big N? Are they going to be less than or greater than?
Less than.
They're going to be less than. Well, less than or equal to, I guess, since I had equal to over there, right? And so they're all going to be on the left of 1 over N. So all the terms in my sequence from here on out are going to be over here.
True.
And so if 1 over big N is in the open ball, all those terms are definitely in the open ball.
So your entire sequence is in the open ball.
Not the entire sequence. X sub 1 wasn't. X sub 2 wasn't. Maybe X sub 3, maybe X sub 4, maybe X sub 5. I don't know. I know that there came a point, namely X sub big N, such that from that point onwards, all my terms were for sure in there.
Okay, I see.
Because I know 1 over big N is less than epsilon. And so 1 over little n is less than epsilon, as long as little n is greater than or equal to big N. Sorry, I didn't really explain the slide. So going from here to here. So then for all little n greater than or equal to big N, 1 over little n is less than or equal to 1 over big N. If I make the denominator bigger, I make the whole number smaller. So if my little n is greater than or equal to big N, then 1 over little n is less than or equal to 1 over big N. But I know 1 over big N is less than epsilon. Epsilon is the boundary on my ball.
Yeah.
If 1 over big N is less than epsilon, it's inside my ball. And so all the points after it are also inside my ball.
Okay.
Because they also are less than epsilon.
Yeah.
And so I have 1 over little n is inside my open ball for all little n greater than or equal to big N. So there came some point in my sequence such that from that point onwards, my whole sequence was guaranteed to be inside my open ball.
Why doesn't it include epsilon? Where you have 1 over small n is less than or equal to 1 over big N is less than epsilon.
Why isn't it less than or
Why
equal to
can't-
epsilon?
Yeah, why can't 1 over n be epsilon?
Well, by definition of the Archimedean property, there exists some integer bigger than any number you can think of.
I see.
So if n is bigger than 1 over epsilon, then 1 over n is less than epsilon. So it's just a consequence of the algebra here.
I see.
So I'm guaranteed 1 over n is less than epsilon. And I'm guaranteed if you make that denominator bigger, you only get a smaller number. All the terms in our sequence are what you get when you make that denominator bigger. All the terms in our sequence from x sub big N onwards. So in other words, x sub 1 maybe not in the open ball. X sub 2 maybe not. X sub 3 maybe not. But if we keep listing it out, eventually we get to x sub big N. That was in our open ball. And now the next term, x sub big N plus 1, is also in it. And x sub big N plus 2 is also in it. Dot, dot, dot. From there on outwards.
I got that, yeah.
Okay. So that's what it means for a sequence to converge to a point. It means you can find some point in the sequence such that from that sequence... Say that a little bit wrong. What does it mean for a sequence to converge to a point? It means for any neighborhood you choose around that point. I can find some term in the sequence such that from that term in the sequence onwards, we're guaranteed to be in that neighborhood.
Okay, I follow.
In our case, our sequence was 1 over 1, comma, 1 over 2, comma, 1 over 3, comma, dot, 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 comma, 1 over big N, comma, 1 over big N plus 1, comma, 1 over big N plus 2, dot, dot, dot. This was our concrete sequence. So I know that 1 over big N is less than epsilon, and so it's inside our open ball. And so all the terms that come after it are also inside our open ball. And notice that for any neighborhood, it doesn't matter how small you make epsilon. If you make epsilon smaller, the only thing that does is it makes so I have to choose a bigger n. So it doesn't matter how small you make that open ball around 0, I can always find an n big enough such that 1 over n is less than epsilon. That's a little trick to it. So then for all, we already said that. Say it one more time. Then for all little n greater than or equal to big N, 1 over little n is less than or equal to 1 over big N is less than epsilon, which means 1 over little n is in our open ball for all little n greater than or equal to big N. Since our open ball is a subset of our neighborhood, then all our 1 over little n is in our neighborhood for all little n greater than or equal to big N. If they're in the open ball, they're in the neighborhood. And so we just really showed that for any neighborhood containing 0, I can always find some positive integer n, big N, such that our sequence is in that neighborhood from big N onwards. Lot to swallow.
Oh, and then that shows the limit. Gotcha.
Right, that's the definition of the limit.
Yeah.
And so the limit, so I write the therefore clear down here. Therefore the limit as n approaches infinity of 1 over n is equal to 0.
What's the little thing you have in between?
The little thing I have in between is a calculus way of doing it.
Okay.
So this is how you do it in topology class. Here's closer to how you do it in a calculus class. So calculus class, we're looking at this definition. We're showing that for any epsilon you choose, I can find some positive integer n, such that our sequence is within epsilon of x from that point onwards. Same thing that we set up there. This is just limiting to ourselves, limiting us to the case of the Serent topology on R. So this is a special case of that definition. This is true for every topological space we're ever talking about. This we're looking at the special case we're talking about the standard topology on R. So this would work in a calculus class, but it's not the way they do it. They do it this way. They use this definition for a limit rather than this one. They say logically equivalent things. All right, so looking at this definition, I need to show that for any epsilon you choose, I can find some positive number big N such that the distance from our sequence to x is less than epsilon from that big N onwards. Now it's always helpful to think about it in terms of our concrete thing that we're trying to show. We're trying to show this sequence converges to 0. So what am I trying to concretely show? I'm trying to show that for all epsilon greater than 0, there exists n in the positive integers such that our sequence, which our sequence in this case is 1 over n, minus the point it's converging to, which is 0, is less than epsilon for all n greater than or equal to n. Sorry, I know my handwriting got atrocious. My arm's tired. Okay.
Oh, your x is 0.
Your x is 0, that's what we're saying it converges to.
Yeah.
And your x of n is your sequence. So here's concretely what we're trying to show. So, I need to show for any epsilon, I can find the n that makes this true. Okay, so let epsilon be any number greater than 0. Which one? I don't know, but there is one. It's some number greater than 0. And observe that by the Archimedean property, the exact same logic we used up there, there exists some positive integer n such that n is greater than 1 over epsilon. Do the algebra, multiply both sides by epsilon, divide both sides by n. That means 1 over n is less than epsilon. 1 over big N is less than epsilon. Now, observe that for all little n greater than or equal to big N, 1 over little n is less than or equal to 1 over big N. If you make the denominator bigger, you make the number smaller. So if little n is a larger number than big N, then 1 over little n is a smaller number than 1 over big N. Okay, what am I trying to show? I'm trying to show that the absolute value of 1 minus little n, the absolute value of 1 over little n minus 0 is less than epsilon for all little n greater than or equal to big N. That's what I'm trying to show. I'm trying to show for any epsilon, I can find my big N. I found my big N. Now I need to show that this is true for my big N. So now I need to show this is true. So then, I'm looking at 1 over n minus 0. I'm looking at this. I'm trying to show it's less than epsilon when this is the case. So the absolute value of 1 over n minus 0, anything minus 0 is just that thing, 1 over n. Now, 1 over n is always positive. Right? So, the absolute value of 1 over n is just 1 over n. Now, notice what we said up here. 1 over n is less than or equal to 1 over big N for all n greater than or equal to big N. This is less than or equal to this. By definition, we chose big N such that 1 over big N is less than epsilon. So I just already showed that for all little n greater than or equal to big N, the absolute value of 1 over n minus 0 is less than epsilon.
Did you, just to point it out, did you need to go through all those steps in your point 3? Couldn't you have just combined point 1 and point 2 and just threw them all together? Wouldn't the logic still be there?
The whole point of line 3 is to validate this inequality.
So you just
I need to show that
justify-
this exact thing, dot, 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 is less than this for all little n greater than big N.
I know. I'm saying you can still show that with your point 1 and 2. What you're saying is you're justifying it and pointing it out explicitly for us to see where you're going.
I mean, this is a common strategy that you always do anytime you're trying to show anything converges to anything.
Do you see what I'm saying though with your point 1 and point 2? You know that 1 over little n is less than or equal to 1 over n, and you know that
So
1
that's
over
how I
n is
justify
less
this
than
point.
epsilon.
And that's how I
You
justify
already
this
knew
point.
that. Yeah.
Yeah, I knew this and I knew this. So take that. This is doing algebra. That's a step that you should probably take. And justifying that when you take the absolute value, it doesn't change anything. That's a step you should probably take. And then, yeah, that's just combining the two previous lines.
Okay, maybe my question is, why do you need to go through the first 2 steps on point 3?
To show the
justify
algebra.
that? Yeah, but
Here's
you don't need to do that.
Here's what line 3 should have for sure.
Okay.
It should have what we're starting with here. So it should have this. It should have 1 over n minus 0. Should have that for sure. It should have is less than epsilon, comma, for all little n greater than or equal to big N. Because this is ultimately what we're trying to show, right? And then from here on out, I need to show you how I'm combining the previous logic that we've used.
Yeah,
or doing
and
algebra.
I see that perfectly.
Okay. So
So what you're saying is you're just following the definition, basically.
So all I'm thinking in my head is I need to show whoever's looking at this is the case. And so I'm just plugging in all the steps that I think will help them make the connection.
I see. Okay.
So that's big picture what I was thinking in my head. This is how I always think about it. When I go to prove that a sequence converges to a point, I'm thinking in my head, I've got xn minus x, and I need to fill in this. Make sure this is the case. Okay, anyways, so what did we show? We showed this exact thing, except for in our special case. Our sequence minus our point is less than epsilon for all n greater than or equal to big N. Therefore, or then, what did we just show? We showed that for every epsilon, there should be epsilon greater than 0, but usually everyone understands epsilon's typically uses a small number greater than 0. So for every epsilon greater than 0, there exists some big N in the positive integers, such that that absolute value is less than epsilon from little n onwards. And therefore, the limit as n approaches infinity of 1 over little n is 0. And that's what you do in the calculus class.
When do you go over continuity in this class? Like which chapter?
Continuity. Our next chapter is on subspaces. If I'm talking about functions between subspaces, it's probably the next chapter.
How many chapters are there?
How many chapters are in the book? No, continuous functions, chapter 4. Okay, so we'll do subspace topologies in chapter 4.
Okay.
There's 14 chapters in the book. To cover what's the equivalent of a Topology 1 course would be to do the first 7 chapters.
Topology is a 2-year class, right?
You can do a Topology 1 and Topology 2. Same way you can do, I mean, you get a calc textbook and we break it up into calc 1, calc 2, calc 3. So it's a very standard thing to take a textbook and break it up into parts. Real analysis, you typically do real analysis 1, real analysis 2. So
You're saying that we go over the epsilon delta definition in continuity, correct?
yes, for sure.
Just like in calculus?
Just like in calculus. The same way that this was probably an exact problem you solved in calculus. Yes?
Is there any particular reason we use the sequence 1 over n?
No, we were just picking a sequence and showing it converges to 0. I could have just as easily shown that the sequence 2 over n squared, the limit of this, as n approaches infinity, is also equal to 0.
But not every sequence converges to 0.
No, I could have shown that the sequence n squared over 2n squared plus n converges to 1/2.
Okay. Okay.
That's for prior knowledge, right? Not off the top of your head.
It's off the top of my head because this n is nothing compared to n squared. What is 100 compared to 100 squared? 100 squared is 10,000. 100 is nothing compared to 10,000. By the time you're looking at a million compared to a trillion, it's a joke to compare the two. A trillion is so much bigger than a million,
Yes.
right? So as n gets really, really large, this plus n here, it does nothing. It's useless. Makes no difference. And so you're left with n squared over 2n squared. The n squareds cancel out and you're left with 1/2.
Oh,
So what about small?
Huh?
well, that actually makes a lot of sense.
It says, as
It's
n
what converges
approaches
to.
infinity.
As n approaches infinity, this gets arbitrarily close to 1/2. Any neighborhood you pick around 1/2, there comes a point in that sequence such that it's arbitrarily close to 1/2.
Do you need the plus n then?
No, the plus n doesn't change anything. That's what I'm saying. It has no effect on the growth of this thing. Because compared to n squared, it does nothing.
Well, it depends on what you substitute for n.
Yeah, n's 2.
Guys, n is approaching infinity.
Oh, okay.
And it's
So
getting,
plug in infinity, basically.
what we're saying is,
Yeah.
so in the standard topology on R, pick some point, or here's 1/2. Make any small neighborhood around 1/2 you want. If you plug in numbers for this large enough, you're going to get arbitrarily close to 1/2. Let's just plug in some numbers just to get a feel for this. When we plug in 1, what do we get?
2.
No.
1/3. Come on, guys. When we plug in 2, what do we get?
1/5? No.
We get 4 9ths.
So
What are we plugging in?
and
4 10ths.
So 2/5.
4 times 2.
What's 2 squared?
Yeah. 4.
Plus 1.
Times 2
8.
plus 2. 10. All right. Let's go on now and plug in something like 100.
big number.
That is going to be 10,000.
No, 20,000, right?
10,000. I did the numerator.
Oh, sorry.
Over 20,000 plus
Plus 10,000.
plus 100.
Oh, plus 100.
Now, 10,000 over 20,000 is almost exactly half. But you added 100 to the denominator. Okay, that hardly changes 20,000. Right? What did it come out to as a decimal approximation? Did you plug that in?
I did.
What is it? Huh?
100 over 201. I think if I did it right.
Oh, you don't have it
I can
giving
do
you
that.
approximate.
I can
Make
do
it give
that.
you approximate.
0.497512.
0.4975. So we're getting really close to 0.5, which is 1/2.
Yeah.
All right,
Yeah.
let's up the ante. Let's plug in 1,000. So up here we get 1,000,000. Down here we get 2,000,000. And we're going to add 1,000. So you're going to look at 1,000,000 over 2,000,000 and 1,000.
Don't work this out.
1 times 10 to the 6 divided by 2 times 10 to the 6 plus 1,000 is how I'd write it.
It's 0.49975.
It's 0.499 what?
700?
There's 3 9s at that.
99975. Okay, we're getting stupid close to 0.5,
Dang. Yeah.
right?
That was fast. Oh, relatively fast.
We go plus n and never actually go over 1/2.
No, it will never go over 1/2. Getting rid of n gets us exactly 1/2. So having the n down there brings us just slightly less than 1/2, just barely less.
Why is that n? Is that
We made the denominator slightly bigger, and so we made the whole number slightly smaller. Without that, it's exactly 1/2.
which is what we don't want, I guess?
Well, the point is, it's getting arbitrarily close to 1/2.
And it never will be 1/2.
And in this case, it never will be 1/2. It gets arbitrarily close. But notice that the limit of this sequence is the exact same thing as the limit of this sequence. Limit as n approaches infinity of n squared over 2n squared. Because this sequence is 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. What does it approach? 1/2. You guessed it. This sequence is never quite 1/2, never quite gets there, but in the limit, it converges to 1/2. So some people say in the limit it equals 1/2, but the proper way to say it is the sequence converges to 1/2. It gets arbitrarily close to 1/2. As we keep plugging in bigger and bigger numbers, we get closer and closer to 1/2. How close do we get? What's our margin of error? We don't have a margin of error. For any small margin of error you choose, you say, I want you to get within 1/10 trillionth. I can always find a big enough n such that we're within 1/10 trillionth.
When you say like the limit of 0.99 to infinity is also 1.
Okay, we can do that real quick. Can we just do this? All right, so we're going to prove that 1 is equal to 0.9 with the line above it, which means repeating forever.
I remember this.
We did like 2 classes ago.
Well, I do know that. I mean,
Isn't that what you're saying?
I've seen it so many different ways. I was just relating it to the limit function as well.
They're different concepts,
This little equation.
Okay, they are different.
but yeah, they have that same related idea.
It just seems like they're related.
but yeah, this isn't getting arbitrarily close to it. You could create a sequence where you keep adding it. I could say 9/10 plus, and then make the next term 9/10 plus 9/100, and then make the next term 9/10 plus 9/100 plus 9,000. And I could create a sequence which is like generating this number, and then the generating number converges to 1.
Yeah.
But this isn't a sequence getting closer and closer. This is the whole thing already, written out, all infinite of.
Yeah, right. And
So that's a slight difference.
And yeah, so the reason why 0.9 to infinity is equal to 1 is because there is nothing in between them.
The reason it's equal to 1 is because multiply both sides by 10, and you get 9.9 repeating.
That's one way to prove it. But it's also that if there's nothing in between two numbers, then it's the same number.
I don't want to say nothing in between them.
No number between the two numbers.
Well, you can probably find some.
They're the same number.
Watching on or
That's, I literally was watching a mathematical video and they explained that to me. that the
You
reason-
could, actually, I think you're okay saying that. If the distance between any two numbers is 0, are they the same number? I think you can say that.
That's,
In the sense that means that there is no number right next to another number.
yes, between the, yeah.
There's no number right next to another number. Like, those are the two numbers next to each other. That never happens.
Oh, maybe, no.
So that's why.
Yeah, now, so the reason why it doesn't use the limit function is because between the limit functions, there always is a number in between, what you call it, the neighborhood or whatever, in the neighborhood, there's always a number between what the number to infinity goes to and the actual limit.
There could be. There could always be distance. In this case, there always was a distance. In this case, there wasn't.
Okay, there could be, is a good way to say it, it's, boring, you're right. So like, yeah, so on the one on the left, it's a lot like what we're talking about, the 0.99, whatever. Yeah, kind of. But it doesn't have to be the way.
I could create a sequence that generates 0.999, that in the limit generates it forever, and then when you evaluate in the limit, you get 1.
Yeah,
Yes.
interesting.
But actually, I don't know how to write as a sequence. I'd have to write it as a series. Same concept though. Okay. I think we're up here. Yeah. We're not going to get the boundary today, are we?
Uh-oh.
All right. So now we're going to deal with the special case where we're in the standard topology on Rn. So let A be a subset of our standard topology on Rn. So this could be 3-dimensional space, 2-dimensional space, 1-dimensional space, 10-dimensional space. It's Rn. But in either case, our open sets are generated with open balls. Maybe we're using 1-dimensional ones, 2-dimensional ones, 3-dimensional ones, doesn't matter. That's what gives us our topology. So now, if X is a limit point of some set A, then there must exist a sequence in A such that that sequence converges to X. So in the topologies that we're used to working with, what we mean when we say it's a limit point of a set is there's a sequence in that set that converges to that point. That's what it means to be a limit point. And if we were in a calculus class, that's how we would define limit points. But, or not calculus, that would be real analysis. Real analysis is deriving calculus, so you can almost use those interchangeably. Anyways, so that's what we're proving. I'm going to prove, so let's just write, oh, we already have it. So we know that A is a subset of Rn. So 1, let little x be any limit point of A. I am trying to prove that there is some sequence I can find in A such that it converges to that x. Now, if x is a limit point of A, what do we know about x?
by using your definition.
Where did we write it?
Right.
It's our very first definition. Okay. X being a limit point of A means that for every u sub x minus the point containing x intersects A. How's the best way to say this? Let X be a limit point of A. First, I need to find my sequence and then show it converges to X. Oh, first I just need to find the sequence. Okay. So here is my sequence. So let X in A, comma, and observe that this is because X is a limit point. Because X is a limit point, every open set containing X, every neighborhood of X intersects A. It intersects A at a point other than X. I don't care about that. All I care about is it intersects A. Every open set that contains X intersects A. That's what I know, if X is a limit point of A. So I may come up with one. So observe that the open ball centered at X with radius 1, I'll call this B sub 1. I may come up with a bunch of open balls. The open ball centered at X with radius 1. When I intersect that with A, it is not equal to the empty set. You with me? There is a point in there. Maybe X, maybe a different point, I don't care. There is some point in there. So, big picture, what am I going to do here? I've got A, I have no clue what A looks like. You know? Something. Who knows what A looks like? And I've got X, which is some limit point of A. Could be anywhere. Here's X. Some limit point of A. What am I trying to do? I'm trying to show that I can find a sequence in terms of A that converges to X. Here's the first way I'm going to do it. I'm going to take the open ball centered at X with radius 1. The open ball centered at X with radius 1 might be like this. Notice it's not necessarily a subset of A. I'm guaranteed it intersects A somewhere though, because X is a limit point. So where the ball B1 intersects A, I'm going to call the point X1. So I'm guaranteed that there is some point X1 in the ball centered at X with radius 1. So let X1 be in there. Now, I'm going to pick a ball with the radius of, let me write that a little bit smaller. So X1 is in that. Now I'm going to take a ball with radius 1/2 and intersect it with A. So now take the ball with radius 1/2. I'm guaranteed that ball intersects A somewhere. Call one of those points X sub 2. Now do it with the open ball with the radius 1/3. Call that X sub 3. And then 1/4. Call that X sub 4. Dot, 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 dot. That's how I'm generating my sequence. So, observe that there is a point X sub 1 in this intersection, X sub 2 in this intersection, dot, 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 X sub n in the open ball, B sub n, centered at X with radius 1/n, intersected with A.
As long as that is not equal to the empty set, correct?
I'm guaranteed it's not equal to the empty set, since it's a limit point.
By
If
definition.
X is a limit point, then any neighborhood intersected with A is not empty. This is any neighborhood once we remove the point X. But if any neighborhood when we remove the point X overlaps A, then any neighborhood overlaps A.
Yeah.
If it overlaps it when we don't have X in there, it still overlaps it when we do have X in there. Because X only increases the places we could have overlapped. You can't get rid of it if we put something in. So yeah. So dot, dot, dot. 2. Then X of n is a sequence in A. So far, I showed that all the terms in our sequence are in A. I grabbed a bunch of arbitrary terms, no clue which ones they are, but they're definitely all in A since I intersect with A every time. And I know that the first term is within 1 of x. I know the second term is within 1/2 of x. I know the nth term is within 1 over n of x. Dot, dot, dot. So that's what I know about our sequence, whatever it is. I know that x sub 100 is within 1/100th of x, because it's in the 1/100th open ball. So that's my sequence. It remains to show that this sequence converges to x. So what are we trying to show? I'm trying to show that if x is a limit point of A, then there is some sequence out there such that it converges to x. There's infinitely many sequences out there. I just need to find one sequence. There could be infinitely many, I just need to find one of those many. So I just need to show that there's at least one sequence we can find that converges to x. So here's our sequence. I'm going to show the sequence converges to x. How do I show converges to x?
The limit as n approaches infinity.
So now we need to use our limit definition. I need to show that for any neighborhood containing x, I can find some big N, such that from big N onwards, our sequence is in that neighborhood. So now I need to grab some arbitrary neighborhood containing x. So 3. Let u sub x be any neighborhood of x, obviously, not of something else. So here's any open set containing x. We already proved a while ago that if there's an open set in the standard topology containing a point, we can find an open ball centered at that point inside the open set. If I have any open set in the standard topology, and you pick any point in there, there's always a small enough ball I can create centered around that point, such that that ball is entirely in the set. That's going back a few lectures. I don't remember when we did it. But 4. Then there must exist some open ball centered at x with radius epsilon. We'll know epsilon. Some open ball with some radius, no clue what it is, such that x is in that open ball, obviously since it's centered at x, and that open ball is a subset of our open set. I'm going to show that all the terms in my sequence from some term onwards, I'm going to find some term in our sequence, x sub big N, such that from that term in our sequence onwards, we're always in that ball. And therefore, we're always in that neighborhood. And so I showed that for any neighborhood you choose, I can find a term in the sequence, such that from that term in the sequence onwards, we're always in that neighborhood. Therefore, a sequence converges to the point you create that neighborhood around. Okay. So 5. By Archimedean property, there exists big N in the positive integers such that 1 over epsilon is less than big N, which is the same thing as 1 over big N is less than epsilon. Right?
Yep.
Then, how can I say this? Maybe observe another fact really quick. Observe that the ball centered at x with radius 1 over little n is a subset of the ball centered at x with radius 1 over big N for all little n greater than or equal to big N. Wasn't thinking ahead. The ball centered at x with radius 1 over little n is a subset of the ball centered at x with radius 1 over big N, comma, for all little n greater than or equal to big N. Right? If I make the radius, the balls are all centered at the same point, right? And so if I make the radius of the ball smaller, it's going to be inside the ball with the bigger radius. So as n gets bigger, our radius gets smaller. And so the smaller ball, if they're all centered at the same point, the smaller ball is always contained in the bigger ball. So observe that this ball is a subset of this ball for all little n in X. Then X sub n is in that ball is a subset. Probably should have just written it all out. I thought if I wrote it all in one go, I would have lost you, but now I realize I'm stupid because I'm writing the same thing twice. So then, our nth term in our sequence is always inside the ball it came from. Look at how our terms are defined.
Yep.
That x sub 1 is a point that's both in that open ball and in A. X sub 2 is a point that's both in that open ball and in A. X sub n is a point that's in that open ball and in A. So x sub n is always in the open ball centered at x with radius of 1 over little n. So that ball is a subset of that for all n greater than that. 8. Then x sub n is in u sub x for all n greater than or equal to n. This open ball was a subset of u sub x. So our sequence is in our neighborhood from little n onwards. And we're done. Therefore it converges. Therefore, the limit as n approaches infinity of x sub n is equal to x. That's what we were after. We just barely showed that for any neighborhood you choose, I can find some big N. For any neighborhood you choose, I can find some big N, such that from that big N onwards, our sequence is always in the neighborhood.
If it's a limit point, right?
If it's a limit point, yes. Thank you. So we chose x such that it was a limit point. And so this is meant to give you intuition for why we call that limit points. Why is that a limit point of A? Because you can always find a sequence in A that converges to it. That's why it's a limit point. Now, this notion of a limit point was developed before we made topology more broad. Topology started out more specifically focusing on calculus and got more and more general. And so it turns out that this happens to be the case when we're on the standard topologies in R sub n. It's not always the case, but this set was already called a limit point before then, and so for historic reasons, it keeps the name. Okay. I think we have one more thing to do for this section, a pretty easy proof, and then we won't get to boundaries, unfortunately. But it's good to take all the time we need, so don't feel like, oh no, we didn't cover what I had planned, so you need to not ask questions next time or whatever.
I do have a question, Donnie, but I think it might be better if we take it off camera so I can outline it better for you.
Okay. All right, next one. Our favorite type of topological spaces, Hausdorff topological spaces. What's a Hausdorff topological space?
Hausdorff.
Any 2 points, x and y, can be housed off from each other. Or in other words, they can have their own completely separate neighborhoods. If you got 2 points, you can give them their own neighborhoods. They can be nice and housed off from each other. Okay, so that's a Hausdorff topological space. These Hausdorff topological spaces are going to have a lot of nice properties. One of the nice properties of a Hausdorff topological space is if a sequence converges, it only converges to 1 point. It doesn't necessarily converge to more than 1 point.
Could it have converged to one point?
That is a wonderful question. Let's look at one really quick. Let's look at R together with the trivial topology.
Yeah.
Pick any sequence in R, and it converges to any number in R. Because every neighborhood of that number, so let's pick a sequence. We'll pick the sequence 1 over n. Okay, there's a standard sequence we've been working with. And let's pick a number, 13. It converges to 13. How do I know? For every neighborhood containing 13, well, there's only one neighborhood containing 13. For every neighborhood containing 13, there is a term in that sequence such that it's in that neighborhood from that point onwards. Every neighborhood of 13 contains the whole sequence. So the sequence converges to 13. And it also converges to 89 and 25 and pi. It converges to every real number. So over here, the limit as n approaches infinity of 1 over n is equal to whatever real number you want to stick there. It converges to anything. So another name for the trivial topology is also called the chaotic topology. And it's chaotic because of this. Everything converges everywhere. So that's where it also gets that name. Most people call it the trivial topology. Occasionally you hear it called the chaotic topology. That's fine. So yeah, it's these special topologies, these ones that are Hausdorff, that get this property that it only converges to one point. Now the standard topology on R is obvious. All our standard topologies on R1, R2, Rn are always Hausdorff. And so they have this property.
The trivial topology is not a Hausdorff topology.
No.
Okay.
Trivial topology, so our only open sets are this and this. Or more generally, the whole set X, right?
Right.
So pick two different points in X. Call it A and B. We need to be able to find two disjoint neighborhoods containing each of them. The only neighborhood that contains this is X, which also contains that, so you can't do it.
Okay, right.
Okay, so if X is a Hausdorff topological space, then any convergent sequence, X of n, in X converges to a unique point. All right, how are we going to prove this? Let X of n be any convergent sequence so I'll let X of n be any convergent sequence. How do I prove it only converges to one thing?
If you just said that it was convergent sequence.
I know it's convergent, so I already know it converges to at least one thing. That's what it means to be a convergent sequence.
Oh,
How do I prove it only converges to one thing? There's a standard way that we prove something doesn't have more than one. We assume by way of contradiction it does have more than one, and we get contradiction. Okay. So if it converges to more than one thing, it for sure converges to how many things?
At least one.
If it converges to more than one things, it converges to at least how many things?
Two. At least.
Two. So assume by way of contradiction that it doesn't only converge to one thing, or that it converges to at least two different things, X and Y. So assume by way of contradiction that X of n converges to both X and Y, where X and Y are different things. X is not equal to Y. All right, you understand how that's a contradiction of what we're after? Okay, so if it converges to X, what does that mean? It means that our sequence has to be getting really, really, really close to X. But if it converges to Y, what does that mean? It has to be getting really, really, really close to Y. And so here's our picture here. Here's X, here's Y. This is an impossible picture. We're showing that this leads to contradiction. Now, so I've got my sequence. Wherever it starts out getting arbitrarily close to X, while simultaneously getting arbitrarily close to Y. I'm guaranteed X has its own neighborhood, and I'm guaranteed Y has its own neighborhood. If our sequence gets arbitrarily close to X, there has to come a point in the sequence where from that point onwards, we're always in the neighborhood. And if it gets arbitrarily close to Y, if it converges to Y, there has to be a point in the sequence such that from that point onwards, it's always in Y's neighborhood. So I'm going to call this use of X. I'm going to call this use of Y. So 3. Let use of X and use of Y, let these be neighborhoods such that they don't intersect. How do I know that I can find those neighborhoods? Because we're Hausdorff. So I'm guaranteed that those two neighborhoods exist. Okay. 4. Since the limit as n approaches infinity of x over n is equal to x, I'm given that there exists some number, I'll call it n sub x, in z plus, such that our sequence x over n is in this neighborhood, u sub x, for all little n greater than or equal to n sub x. Shouldn't have drawn my picture so far up here. Let me draw my picture over here again, because I think it's a useful picture. So we got x and y are two distinct points. I know that my sequence, here's x of n. Drawing an impossible picture, but here's x of n, our sequence. We know that there's some neighborhood around x and some neighborhood around y, such that they don't intersect. Since our sequence gets really close to x, what am I guaranteed? I'm guaranteed that there's some term in the sequence, which we're going to call the x, this term right here, I need to draw it down here, is the x sub n sub x term. From the n sub x term onwards, we're in this neighborhood. Not the first one, not the second, not the third, not the fourth, but the n sub x term onwards, we're always in this neighborhood. That's what it means for this sequence to converge to x. There has to be some term such that from that term onwards, we're always in that neighborhood. So since the limit, since x of n converges to x, there must be some positive integer, we're calling it n sub x, such that for every term in the sequence after that, we're in u sub x. And then same logic again. Since the limit as n approaches infinity of x of n is equal to y, that gives me that there exists some positive integer, we'll call it n sub y, in z class, such that x sub n is in u sub y for all n greater than or equal to n sub y. Right? So, I know that there's some term in over here, some term, call it x sub n sub y, such that from that point onwards, we're in that neighborhood.
Okay.
6. Let big N equal the max of n sub x and n sub y. So big N is whatever's bigger out of those. We know that from n sub x onwards, we're always in here. And that from n sub y onwards, we're always in here. Maybe this is like 5,000 and this is 8,000. I know that from 5,000 onwards, we're in here. And from 8,000 onwards, we're in here. Therefore, from 8,000 onwards, we're in both. We're in here from 5,000 onwards, which means once we get into 8,000, we're still in here.
Yep.
We're in here from 8,000 onwards. So from 8,000 onwards, we're in both. So if we're in here from n sub x onwards, and we're in here from n sub y onwards, and big N is whatever is bigger out of those two, then we're in both of them from n onwards.
But then that shows that the two neighborhoods.
This is an impossible picture.
Yes.
Yeah, like what you're saying and what you're describing, that's not visually.
So since our sequence converges to x, then there has to be some term in our sequence. We're writing out all the terms. Our first term is x sub 1. Our second term is x sub 2. Our third term is x sub 3. Dot, dot, dot. There has to be some term in our sequence such that from that term onwards, we're always in u sub x. That's what it means for the sequence to converge to x. For any neighborhood around x, our sequence from some term onwards is always in that neighborhood. So I'm guaranteed that if we keep going along, we'll eventually get to some x sub big N sub x, comma, keep going, such that from here onwards, we're always in here.
Okay.
Now, same thing over here. Since this converges to y, I'm also guaranteed that from x sub n sub y onwards, we're always in here.
It just makes me, it seems like y is a smaller circle inside of x is all I can imagine when you're saying that.
That is the only way we could possibly make this true. This is an impossible picture. We're showing this is impossible.
Oh, okay.
And so, yeah, you're struggling with the fact, how's that possible? It's not.
I got it now.
Right.
By way of contradiction.
Assume by way of contradiction. So we're saying from here onwards, we're always in u sub x. And we're saying from here onwards, we're always in u sub y. So whichever's the bigger out of these two, from that term onwards, we're always in both. So, because I don't really know which of these comes first. I have no clue. But whichever comes first, let's call that one just big N. So 7. Then, for all little n greater than or equal to big N, comma, x sub n is in u sub x, and x sub n is in u sub y. Contradiction.
Yep.
Because there's nothing in u sub x and u sub y.
U sub n x and n y for
X sub n is in u sub x, and x sub n is in u sub y. That's supposed to be y.
That shows that their intersection, Chandler, has something in it.
Right.
yeah, but you wrote nx and ny, and now you're using ux and uy. Am I seeing that wrong?
That's a u sub x, that's a u sub y.
Usually good.
Alright, so that's contradiction. We have something in u sub x and something in u sub y, but u sub x and u sub y have nothing in common. So contradiction. 8.
And
Therefore,
X is equal to Y.
X sub n, well, we don't know which one it converges to. All we know is that, therefore, x sub n converges to a unique point. Because it can't converge to 2. Wait, why can't it converge to 3? I only proved it can't converge to 2.
Because it had to be at least greater than 2.
Oh,
Because if it converges to 3, it for sure converges to 2. And I showed it can't converge to 2. So it can't converge to 3.
right.
Okay, how do I know it converges to anything? We said we show it converges to a unique point. How do I know it doesn't converge to nothing?
That's not a point.
Because by definition, you know it converges to something.
Yeah, because we said let it be a sequence that converges.
Yeah.
Any convergent sequence. By definition of a convergent sequence, it converges to something. Otherwise, it's not a convergent sequence. So I know it converges to something, and I showed it can't be two things. So we handled all possible cases.
Okay.
Okay. Just want to make that clear. Okay. We're out of time. Let me just give you really quick the definition of a boundary, and then we'll reintroduce it next time. That way you get the definition twice. So our next section is going to be on boundaries. So let X be a topological space, and let A be any subset of X. Then the boundary of A, which we use a delta symbol there. I'm pretty sure none of you have seen partial derivatives, right? So no one will be confused by a symbol. Okay, good. Okay, so that's just a delta. Lowercase delta in the Greek alphabet. So then the border of A is equal to the closure of A minus the interior of A. And it's exactly what you would think of as being the border if I never even asked you, if I never even gave you that definition.
Yep.
So coming down to this picture, here's A, right?
Yes.
Really quick, what's the closure of A? It's the circle including the edge, right? What's the interior of A? It's the open ball like that, right? Containing all the points inside. If I take the closure and I subtract the interior, what am I left with?
Boundary.
Just a circle, right? No points inside, no points outside. Just a circle, which is the boundary. If I were to ask you, what's the boundary of A? You'd say, this circle, right?
No.
So fill in.
Oh, you wouldn't have said that? I assumed you would have. Well, that's what it is.
It is.
Yeah, it's the circle around A. It's the closure minus the interior, which leaves you with just a circle.
But the left side of your circle is open.
Yeah, the right side's closed.
Am I confused?
But that's still the boundary. Think about the boundary is what is right on what's in the set and what's not in the set, right? The boundary. It's right smack between the two.
So it doesn't matter if it's open or closed.
So this is right there on the boundary between the set. If the set's going to have a boundary somewhere over here, it's got to be that point, right? That point's got to be on the boundary.
But the closed part is included inside of the.
Right, so the point either has to be inside or outside the set. But in a sense, it's touching both the inside and outside. It's a boundary,
I see.
right? You go, you build a fence around your yard. The fence is on someone's side of the property line, but it's still the boundary, right?
Yeah.
So this point happens to be in A, this point happens to not be in A, but they're boundary points. They're kind of both touching in A and not in A, in a sense.
So, why does it matter if it's closed and open then? If it's just the boundary?
It's just a boundary. So it's the closure minus the interior, and that leaves you with just a boundary. Here's the closure. It's everything including the boundary. Here's the interior. It's everything except the boundary. You take everything including the boundary and get rid of everything except the boundary, and you're left with the boundary. It's the language we've been
That's
using the whole
obvious to
time.
me, But I'm still confused by your example. Wouldn't it just be like half of the circle? Because that's what the closed boundary is. I get that you're saying that it's close to the edge right there. But if you really look at it pictorially like you're saying, then that doesn't add up to me. If you take your closed set and you take everything
So-
that's open inside of it, you're only left with that half of the boundary.
If you take your the smallest closed set containing this includes the boundary.
Yes. And then you take your open set out of that.
Your smallest, this isn't an open set. This is A.
It's closed.
The smallest open set inside of it is right there.
Yeah, that's what I'm saying. Take
So-
that out.
Here's this. Remove the insides,
No.
and you're left with just a
You
boundary.
don't start with that though, you start with that.
Yes, but in your
The
set A,
definition of a boundary is a closure minus the interior. It's not A minus the interior.
Oh.
So yes, if you want A minus the interior, if we were doing that, then yeah, you'd be left with this weird semicircle thing.
okay, I see it now.
It's the closure
That's
minus the
very
interior.
obvious.
But think about why it makes, there's no good reason to count this as part of the boundary, but not count this as part of the boundary.
It's closed.
Because the boundary should be what's between in the set and not in the set, right?
Yeah.
So this is the last point still inside the set. This is the first point no longer in the set.
Okay. So then, when you're talking about boundary, whether the boundary is closed or open is irrelevant.
A boundary is always closed. And we'll prove that.
Okay. Okay, I'll wait for that.
It's always a closed set. Don't think that means it's always a closed loop.
Okay. That makes
Turns
more
out
sense.
in R2 it will always be closed loops.
Okay.
A closed loop or multiple closed loops.
In a way, it's kind of just getting slightly wider on the.
The- It's kind of okay to think about the closure of a set making it slightly wider. Kind of. Because when you talk about the rationals, what's the closure of the rationals? The rails. That's not slightly wider anymore. You more than doubled it. You increased it the magnitude of infinity that it is. That's a lot more than doubling, right? Because the reals is a whole different magnitude of infinity than the rationals. The naturals, the integers, and the rationals, they're all the same size. The reals, it's a whole new beast. So yeah, when you do that, that's not slightly wider. That's not even doubling it. That's scaling it up to a whole new infinity. But in the standard topology on R2, that's usually how it works out. What's the closure? Just fill in those points that are bugging you, right? There you go.
Otherwise, we're gonna go mad. It's the only way to think of it.
A lot of, when this stuff was being developed, it was for the standard topologies. And so a lot of the language that we use makes perfect sense with the standard topologies. But when you deal with other topologies, not so much. Or sets, I shouldn't say that, because that was still in the standard topology. I'm lying to you that. Most of the sets we care about in the standard topology, that's the case. This is still a set in the standard topology, Q. It's just we're hardly ever doing an analysis of the set of rationals in calculus. We're dealing with nice continuous sets, and we'll find out what that means, but those are the ones we like. Anyways, jumping way ahead. So that's a boundary, and then we'll restart by introducing that definition next time, go over some feel-good examples, a couple proofs, and then we're done with boundaries and on to chapter 3. That's why I was hoping we'd get through all of it today, but that's not going to happen.
You're saying there's some, you don't have to record this if you don't want to,
Go ahead.
but you're saying there's some balls that don't close all the way?
No,
Oh. Well, you mentioned something like that.
so look at the rationals. It's not a ball in any sense of the word. The rationals in R. So that's not open intervals. but it's still a set in the standard topology on R. So I was saying when you're dealing with nice sets that can be created from unions of open balls, for example, then yes, its boundary is going to be a nice closed shape. So if A happens to be a union of open balls, then that's the case. But remember, union of open balls just gives you the open sets. We're not necessarily just talking about the boundary of open sets, we're talking about the boundaries of sets in general. Okay, so if it's an open set, yes, it's going to be a nice closed loop. Or multiple nice closed loops. Okay, I think that's it for questions. Besides his secret question.